All right. For the video, welcome anyone who's watching from the future, and welcome to those who are in the room and online now as part of this. This is a revision seminar for Introduction to Mathematical Economics, and it's Semester 1, 2021. I've taken some requests, and I've just got another one. I'll add it to the list. Partial differentiation. And I'm going to talk about some of these things that people have asked. And if I get through all of them, then you can ask new things, and I'll keep going till the end of the 2 hours. All right. So the questions I've been given have been mainly about maximizing and minimizing things. This is the one you sent, wasn't it? Yeah. Where is it? I'm just reading some questions. I'll be with you in just a minute. Yeah, some of these are the same ones. Okay. So I think what I'm just going to do is talk about those things. And they're going to be different for different contexts. So, yeah. Before I do have a question about two different things. One is, could someone please tell me what MRCS stands for in the context of a utility? Because I don't have access to your course materials, so I couldn't look that one up. I'm presuming marginal something.
Yeah, so it's the marginal rate of commodity substitution, which is the partial derivative of x1 over the partial derivative of x2, I think. Yeah.
Like that?
Like that. Yeah, yeah.
Okay, good, just for future reference. Okay, sweet. All right. Give me a minute to get ready. I sometimes have to take a few minutes to sort things out. So I'm going to start with this example problem. The total revenue is 120Q minus 5Q squared. And at this moment, Q is 5. Then use differentiation to estimate the change in total revenue when Q increases by 0.25. Okay. All right. So I will talk about partial differentiation eventually when we get there, just letting you know. But for the moment, this sounds to me like an ordinary differentiation sort of problem. So the point of differentiation is to figure out how quickly one thing changes when another thing changes. And so I would begin this by doing the derivative like this. So the derivative of 120Q would be 120. This derivative, the minus 5 will still be there because it's multiplied on. And then the derivative of Q squared would be 2Q to the 1. And so I get 120 minus 10Q. And so what this says to me is that a very small change in TR is equal to 120 minus 10Q times a very small change in Q. All right. And so I can estimate if I know that the change, the D stands for difference, if I know that the difference in Q is 0.25, and I know that the current value of Q is 5, then I could sub those into this spot to figure out what the change in TR is. Does your lecturer use a triangle for change? Yeah. So the D stands for an extremely tiny infinitesimal change, like the opposite of infinite, but small. Infinitesimal change in something. And so we're not looking at that, we're looking at a big change. So it's kind of like the change in TR is approximately times the change in Q. That's how I write it on paper. It's always nice to try and match what your lecturer does because everyone uses slightly different notation, but this is how I do it. And so that would be, because at the moment the Q is equal to 5, I can put that in. And the change in Q is 0.25. And so this would be whatever it works out to be. 120 minus 50 would be 70. And that would be whatever a quarter of 70 is, 35. 17.5. That's what calculators are for. I was right. Okay, so this is saying that when the quantity increases by 0.25, the total revenue goes up by 17.5. We don't really know the units. The quantity could be in thousands and the revenue could be in millions of dollars. We have no idea, so we just have to leave it without units. How do people feel about that calculation that I did?
Good. Yeah, that was good.
Yeah. Oh, good. So there you go. That's the correct answer there. Okay. So I have some questions. It's always useful when you see, when you're basing your learning off of quiz questions, to try and think what would happen if, and to make sure that you still know what to do if it was a slightly different situation. So I'm wondering what would have happened if it was a decrease by 0.25. How would this have been different? Anyone feel free to answer. Did everyone hear that? I don't think you did. It was, we were having a suggestion that maybe instead of timesing by the 0.25, we should divide by the 0.25. Has anyone got other ideas?
Do you just times by negative 0.25?
That's a possibility as well. How does everyone else feel about which option is the one that they would do? It's all right not to answer. I just like to give people the option. So you've both chosen a different opposite. And the correct opposite is a negative 2.5. So that's saying that the change in Q is actually down by 0.25. And so that means the change in TR would be approximately by minus 0.25. And so that's all going to work out to the exact same thing, but with a minus 17.5. So these are really important questions to ask yourself when you're looking at things. I'm going to try and do it for all of them, just do some what ifs. I don't feel like doing any other what ifs here, but if anyone thinks of these sorts of things with any of the problems we're doing, say, well, what if it was different in this way? Please do ask. That's really important if it's a thought you have. I will add something else. The rules are in this sort of seminar, it's for you. So if you have a question that's relating to what we're doing, feel free to chime in and say it. If I'm in the middle of a calculation and you think I've put a minus in the wrong spot, please tell me. It's okay to interrupt me to tell me that sort of thing. Don't wait till later and then we find out that I've done the whole thing wrong. Okay, that was a good start. I'm going to choose my next question. We'll just try this one and see what this one's about. So the demand function is P is equal to 40 minus 2Q squared for Q's between 0 and 20. Find revenue at Q equals 5. I'm going to need a little bit of help here. Marginal means the derivative of revenue, right?
Yeah.
But I'm going to have to figure out what revenue is. So my guess, and you can tell me if I'm right, revenue should be the amount of stuff you sell times the amount that you sell it for.
Yeah, so P times Q, I think.
That's the amount of stuff, the quantity sold, and that's the price that you sold it for, right? Okay, so therefore we can create the formula, which is P, which is 40 minus 2Q squared times Q. That's my understanding of that. Okay, cool. Thank you so much for helping me out here. And so the marginal revenue should be the derivative of this. The amount of revenue you get for one extra Q. Okay, so I'm going to have to differentiate this. I've got a few choices for how I could do that. I could expand it out so that, you know, this squared becomes a thing and then multiply by the Q and differentiate that. That's one option. Or I could use the product and chain rules. I'm going to use the product and chain rules because I feel like it. So I've noticed that this is made of two pieces multiplied together. And so the derivative will be the derivative of this bit times keep the Q as it is, plus keep this one as it is, and times by the derivative of the Q. That would be from the product rule. Okay, so the derivative of Q would be 1, because that's the coefficient of Q. The derivative of this, well, it's a squared with something inside it, so I would go that's 2 of 40 minus 2Q to the power of 1. But because of the chain rule, I'll have to also multiply by the derivative of this, which is minus 2. How people feel about what happened there? Feel free to use the buttons in Zoom to stick your thumb up if you're interested. Yay! Okay, and so now I could simplify this, and it's probably not, I don't know how your lecturer feels about this, but I wouldn't simplify it too much. But this 2 and a minus 2 are crying out to be multiplied by each other. And I'd leave it there. Except they've said they wanted to know what the marginal revenue was when Q was equal to 5. And so I would need to sub that in. When Q is 5, the marginal revenue turns out to be minus 4 times 40 minus 2 times 5 times 5 plus 40 minus 2 times 5 squared, which again is what calculators are for. But I can do a little bit. The minus 4 times the 5 is a minus 20. The 40 minus, now 2 times 5 is 10, that's 30. And this is 30 squared. So I've got 900 minus 600, which will be 300. That's my guess at the answer, but I'm going to ask my calculator too. Sorry? I forgot mine. Do you know what calculator you're going to be allowed during your exam? Okay, do you think you should look up the instructions? At some other maths courses, they're only allowed to use the calculator that's on the screen in my uni, but worthwhile checking So we've got -4 times 40 minus 2 times 5 times 5 plus 300. Yes, okay, I was right. I like to try and do it myself first. Yeah, okay. So this is saying that if we have a current quantity of 5, then going up by a very small amount of Q would make the revenue go up by 300 times the amount. So if I went up by 0.1, the revenue should go up by 30, for example. That's what marginal revenue means. It's how far one goes up compared to the other. Cool. Okay. Everyone comfortable with my product and chain rule here? Yeah, cool. Just making sure. Oh, God, that's a good question. 300. Okay, cool. So just to say, there was an alternative way you could have done it. You could have, when you were at this point, you could have done some algebra before you did the derivative and gone like 40 squared minus 2 times 40 times 2q plus 4q squared times q and expanded it all out. That's 1600. That's 160. And you could have done the derivative there like that. So and I really hope that it gives me the same answer. So you don't have to do this other working. I'm just pointing out that it's a possibility. So at Q equals 5, the marginal revenue is this derivative. Oh, that's not a 2. Yeah, that's okay. $1,600 minus 160 times 2 times 5 plus 4 times 3 times 5 squared is also 300. Whew. Awesome. Okay. So this is an alternative way of doing it, which looks marginally faster today. But if this had been a cubed, then this probably would have been faster. So yeah. Yeah. Okay. What's that? Oh, the expanding out? Yeah. It shouldn't matter. It should give you the same answer either way, which was the point I was trying to make. I can see a question there that's been sent to me in the chat. I'll get to that too. I'm just going to compare to what I've been working on. I think I did see that one in your list, but I'm going to do that one as well. Okay, so I'm going to do the one that I was just sent in the chat. Demand equation is P equals 40 minus 2Q. Find the level of output that maximizes total revenue. Okay, cool. Thanks for providing that one. So that's going to require us to find the total revenue, and we know how to do that. We just did that already, so that's good. The total revenue is the price times the quantity, which is 40 minus 2Q times Q. And there are two ways to attack this, depending on whether you want to use derivatives or not. I'm going to do them both, because I'm pretty sure both of them have appeared in your course. So one way is to imagine what this graph is. This is a quadratic function. I don't have to expand it out to do it, but I just want to make sure that it's obvious. So 40 times Q minus 2Q times Q, which is that. That's a quadratic formula, which means this function is a quadratic function, which means it's a parabola. And the Q squared has a negative on it. That's not a Q squared there, that's just a Q, sorry. And so it's tradition to write Q squared first. Q squared has a negative on it, which means it's this shape. And so the maximum of this revenue should be here at this point. So the question is, where is it equal to 0? Because the maximum will be halfway between the places where it's equal to 0, because that's how quadratic functions work. So if I did this, I would probably say TR is 40 minus 2Q times Q, which is quadratic. The maximum is halfway between the zeros. And so I'll find when it's 0. Damn it, I'm just really not doing well. 40 minus 2Q times Q equals 0. That'll happen when 40 minus 2Q is 0, or when Q is 0. And this would be 40 is 2Q, and so Q would be 20. And so the zeros are 0 and 20, and this is what the graph looks like. And so the maximum is halfway, and so therefore the maximum is at Q equals 10, because that's halfway. So that's how to do it as a quadratic function. That's how I'd do it, and I'm pretty sure you did quadratic functions in this course. Yay, okay. You could also do it with derivatives. So if you really wanted to, you could do this, or we've just figured out what the, total revenue, and that was times Q, and we could differentiate it instead, because the total revenue, the maximum of any function can only happen when the derivative is 0. So derivatives, if I found the derivative and figured out when it was 0, that would be the time that the maximum must happen. It could also be a minimum, but I know that this one is this shape anyway, so there's only going to be one place. So the marginal revenue, which is, sorry, I'm so into partial derivatives. So that'll be a 40, that'll be a minus 2 times 2Q. And the maximum happens when the derivative is 0. Which would be (40 minus 4Q is 0). And if I look at that, the only number Q that's going to make that happen is 10. But I can do the actual algebra. Divide both sides by 4. Yep. So maximum total revenue is when Q equals 10. How do you feel about that? I don't know your name. I've only got your ID number. I'm not going to call you by a number. Good. Okay. So the reason I did the derivative one is that would work even if it wasn't a quadratic function. So if we had back here, if we had this demand function and asked when is the maximum of the revenue, then we would have to use derivatives, for that. I want to do it. So doing a what if here, what if it was this? Demand. Zero is less than or equal to Q is less than or equal to 20. Find Q to maximize revenue. So in that case, my total revenue, we already figured it out, it's P times Q. And I already expanded this out earlier because I feel like doing the expand out version. And I already did the marginal revenue. And it was squared. And so to find where the maximum revenue occurs, I would need to figure out when that is equal to 0. So maximum of TR so now I've got this. Which I do not like. It's a quadratic equation and it has lots of big numbers in it. So that is annoying. It's traditional to write a quadratic equation around this way. And I can see 4 goes into everything, so I'll divide by 4 because it's easier when the numbers are as small as possible. And I don't like my chances of factorizing that just off the top of my head, and so I would use the quadratic formula. So this is A, this is B, this is C minus B plus or minus the square root of B squared minus 4 times A times C over 2A. Oh, this is interesting. Just want to see what this works out to under here. Oh, wow, nice. Look at that. It's a square number. Awesome. Don't need the square root anymore. That's 40. And so if it's the plus, it'd be 80 plus 40, which is 120. And if it was a minus, it would be 80 minus 40. And so we'd have either 10 or whatever 40 divided by 12 is. All right, whatever it is. I guess it'll be 10 thirds. Oh, cool. Okay, so both of those are actually possible, which is interesting. Well, I was hoping that one of them would fall outside the zone from 0 to 20, in which case I'd be allowed to ignore it because it doesn't count for the quantities that are possible. The maximum would happen at this place, or when Q is one of the two ends. Yeah, so I'm not 100% sure what's going on here. But this is a cubic, this thing here. And so it'll look something like that, I'd say. I don't really know where this is. And this one is at 10/3, and this one is at 10. But I don't know if it goes below the axis or not. But one of them is a turning point and the other one is another turning point, but it's the other way around because that's how cubics behave. This would turn into a really hard problem. I don't know if this is the sort of thing your lecturer will do to you. Yeah. And so my guess is that the 20 is actually all the way out here. And I have a guess that the maximum maximum revenue will actually happen at 20. Even though this is a maximum nearby, the actual maximum will be over here. So I just have to try them all and see what happens. So when Q equals 0 or 10/3 or 10 or 20, the total revenue works out to be, and I would sub my numbers back into the formula. So when Q is 0, that's good. When Q is 0, that's 0. When Q is 20, oh, I'm going to get 0 there as well, because 14 minus 2 times 20 is 0. Okay, so this one's 0, so they're not the maximum. When Q is 10/3, I'm going to need a calculator for that one. (40 minus 2 times 10/3 squared times 10/3 is 3703. It's an extremely large number. And 40 minus 2 times 10 squared times 10 is 4,000. Oh, I think I have my graph the wrong way around. This is distressing me just a little because this cubic here would make me think it was this way up. So maybe I've done something wrong. Just give me a moment. I'm going to draw this graph on a screen and see what it does. I don't know if you're allowed to use Desmos in your exam, but for now, I just want to make sure that I'm thinking about this correctly. This won't like me using Q, so I'll use X if that's okay. I think I've done something wrong in my calculations. Because I've got a turning point at 20. I've done something wrong. Damn it. Okay, let me go back and see if I can figure out where I went wrong. Oh, I should have known that. A squared means there's a turning point on the x-axis. Yeah, that always happens that way. So if you've got a piece with a linear thing inside it squared, that'll make a turning point that's actually right on the x-axis, either a bottom or a top, depending on what the function's doing nearby. Okay, so I've done something wrong. Let's go back and see if I can figure out where it was. So look at this. You get to see how David decides if things are Oh, don't end the meeting, David. How David decides if things are bad. So the reason, yep.
Sorry, what was that website that you were just on?
That was Desmos.
Okay. Desmos. Okay.
It is a graphing calculator. Very useful.
Yeah.
Especially if you've got a touch screen so you can pinch to change the size. But if you don't, there's actually a this settings here, you can change what the x-axis and the y-axis is that it's showing. So
I see. Okay. Yeah.
And so this one's actually desmos.com/calculator because they've got other kinds of calculators as well. They have a matrix calculator too. I don't know if that's relevant. And you can put in a matrix and put the numbers in and then ask it for the reduced row echelon form and stuff. So yeah, I don't know if that's helpful for this course. I can't never remember what's in which one.
Yeah, I think last week we focused on matrices. They didn't do it.
Oh, okay. Well, it might not be examinable. It's probably in mathematical economics. Not the introduction, but just there's a second semester one. So, all right. That was a very important question, Annalise. Well done. Okay. Let's see where I went wrong, eh? I think the expanding out was right because it produced the correct derivative last time. So I reckon that's okay. And I definitely, the 2 times the 160 is 320 and the 3 times the 4 is 12. And I divided everything by 4 correctly, I think. That divided by 4 is 3. 32 divided by 4 is 8. That divided by 4 is 400. It must be with my quadratic formula that the problem was. Oh, bloody hell. No, that's all right. So minus b, and it was already a minus, that makes it a plus. B squared minus 4 times 3 times 400. Can't see it.
When you square a number, it doesn't matter if it's positive or negative.
No, it doesn't. Well, So let me just check. If I put these both back into the derivative, does it make it come out to 0? 1600 minus 320 times 10 plus 12 times 10 squared is not 0. No, plus 12 times 10 squared is not 0. So this is not a solution. I'm not sure why. Okay. Solution is too small. Finding errors is actually a very difficult skill. Minus b, plus or minus. Minus 80 squared would be the same as plus 80 squared. Minus 4 times 8. Is not 12, it's 6. Damn, what am I doing? 2 times 3 is 6. Right. Okay. Well done. So 40 divided by 6 would be the same as 20 divided by 3. Okay. Right. Try that again. And so now if I try that again, I know that this was a cubic and I know what shape it was. It's a don't really know how high up it is, but it's approximately this shape. And I know that my turning points are at 20 on 3 and 20, which is one of my endpoints anyway. So I don't need to worry about what's going on over here. And so I've got 3 places to worry about. And I'm pretty sure it's going to be here because of the shape of my graph. And so when Q equals 0 and 20 divided by 3 and 20, the TR is this times 0, which is 0. At 20, it was 20 minus 2 times 40 minus 2 times 20, which is 0. And then I'm going to have to ask my calculator what happens when it's 20 over 3. Which is 4,740. So the maximum is definitely here. So to have maximum revenue, Q equals 20 over 3, which is about 6.6. And the maximum total revenue is, 7.4 if we're going to have a, is that. Sweet. Oh, good-o. Problem solved. Thoughts or questions? So I was trying to use my knowledge, my knowledge of what cubic functions should be shaped like helped me to know that I was doing something wrong. Yeah. Cool. So it is sort of just a single hump in the zone we're looking at, which is interesting. Probably why it was chosen as a reasonable price function, revenue function. Okay. Where'd my chat go? Right. I did promise I'd talk about partial differentiation, and so that I will do. I started at 11:30-ish, didn't I? Like 1:45. Yeah. Okay. Give me a sec. There's just a couple of... Okay. So all the rest of the problems that people have sent have been about partial differentiation, but still about finding some stuff. And they're not necessarily maximizing and minimizing. And that was a wrong title to begin with. It's just various problems. But they're all to do with derivatives of some sort. Okay. So this one really is just about partial derivatives. It goes f of x1 and x2 and x3 is x1 times x3 cubed over x2 plus ln of x2 times x3. All right, and find all the partial derivatives. Okay. So partial derivatives are designed to figure out how quickly the function value changes when one of the other variables changes, but the other ones stay the same. So this is just the general idea. This is what I'm thinking in my head. How quickly a function value when one variable changes at a time and the others stay the same. That's what partial derivatives are for. And so that tells you how to do them as well. You do an ordinary derivative because that's what ordinary derivatives do. They tell you how quickly things change. But what you do is you pretend that all the variables that you're not thinking about are staying the same, which means they're constant. And so I've got that. I'm going to remove the x1, x2, x3. And so just want to check some things about notation. I would normally call this df. That would be a partial derivative with the curly d's. Does that look familiar? But an alternative notation is to put a little one at the bottom of the name of the function. Is that something your lecturer does too?
Yeah, we do both, I think.
Awesome. Just checking. So whichever one you like, doesn't really matter. But your lecturer has in the question that I was sent, they used this version. And apparently, if the variables are called x1 and x2 and x3, you can just call it f1. If everybody knows what the variables are called, you can do that. Yeah. These are all the same notation. Okay, so I'm going to do f1, which is the partial derivative of this with respect to x1. So when I look closely at this, I can see that this and this count as constants because they don't involve an x1, and these both count as constants. So when I differentiate with respect to x1, it's the same as x1 times a constant. And so if I had x1 times 5, the derivative would just be 5. And so if I have x1 times this constant, the derivative will be that actual constant. And this is a constant from the perspective of x1 changing. And so the derivative of a constant would be 0. So that's f1. Right. So f2 would be df on dx2. Now, that one's not as easy to do. All right, I'm going to rewrite my function on the next page because I don't have the space. So f is x1, x3 cubed, and that x2 would count as x2 to the negative 1. I find it easier to do derivatives when it's written as a power. So I'm just going to write it like that for the purposes of this one. So then f2 would be df on dx2. So this is a constant multiplied on, so it will still be there afterwards. And then I will multiply by the current exponent and put the exponent down by 1. And then the derivative of ln is 1 over the thing. But I have to multiply by the derivative of this, which will be the constant that's multiplied by x2. So it'll be that. And so I get minus x1, x3 cubed on x2 squared, because that minus 2 will put it down the bottom there. And then x2 divided and x2, the x2 is there still. but the x3s will cancel because I divided by x3 and multiplied by x3. So that's my answer for df on dx2. Okay. And I'll just go back to the original formula. So now f3, I can do this one. The x1 on x2 counts as a constant. And I'll have multiply by the current exponent and put the exponent down by 1. And then I'll get the exact same thing going on here that happened here. It'll be 1 over that thing. But because of the chain rule, I have to multiply by the derivative of that with the x2 being a constant this time, so I'll get the x2. Right, so those are all the first partial derivatives. I'm not sure I really want to go through all the effort of figuring out all six of the second partial derivatives, but I'll do a couple of them.
Wait, sorry, I'm a bit confused.
Yes, go.
When you've got f of 2 there, yeah, that one. So what's happened with the, why has x1, x3 to the power of 3 gone over the x2 squared?
Oh, here.
Yeah.
So this is all multiplied together. And x2 to the negative 2 is the same as 1 divided by x2 to the plus 2.
Oh, okay.
And so, yeah, multiplying by something to the power of negative 2 is the same as dividing by that thing to the power of positive 2.
Okay, yeah. And then here, and then for the 1 over x2, is the timesing by the x3 cancelled out the x3 on the denominator? Is that why it's...
Correct.
Yeah.
So you could think of this as like over 1, and
Okay.
then x3 divided by x2 times x3, and then the x3's cancel.
Yeah, okay, thank you.
That's exactly what it is. These are important questions. You should always ask these sorts of questions. Okay, so they're my 3 first partial derivatives. This one's much simpler than the others. So the second partial derivatives would be starting from one of them and doing another partial derivative. So if I did f11, that would be doing df on dx1 and then d on dx1 again. And that would be written as d squared over dx1 squared. I don't know if you've seen this notation. Yeah, okay, good. But ultimately what that means is it's the derivative of the one that I just got. So just importantly that when you do this one, it tells you that you do, well, I'll deal with that in a second, ignore that for a moment. So this would mean that I'd have to take the answer that I got for F1, that was the answer I had for F1, and I'm going to have to differentiate it again with respect to X1. But this doesn't have any X1s in it, and so that answer will be 0. But F12 would mean starting with 1 first, because it's the one that's closest to the F, and then doing with respect to X2, like that. So I'd have to differentiate that with respect to X2. So I feel like for me it would be easier to write it like this. And so then the x3 cubed will still be there because it's multiplied on. And then I'll have to make this go down another power. And I can do that same move again. Multiplying by something to the power of -3 is the same as dividing by that thing to the power of -3. How do you feel about what happened there?
Sorry, is that 2 on the is that 2 on the numerator, the -2 up the top? Or is
Yeah.
it front? Okay, yeah.
Same thing. So
Oh, yeah.
it could be this, or it could just as easily be this. And they work out to be the same answer.
Okay, yeah.
Yep.
How would you do it without making negative power? Like, would you do it just as a fraction, like in the beginning?
Like back here,
Yeah, and just like,
the quotient rule. Or
yeah.
some people just know that the derivative of this is this. But I'm not using that one. So you could.
It's a very long.
Oh crap! It wasn't -2 to begin with. Curse me. Sorry, that was a -1.
Yeah.
Well, that makes this a -1, and this a -2, which means that that -2 is totally not there at all. Damn it! Just getting ahead of myself. Right, good noticing. So if you happen to know already that 1 over x, when you do the derivative, becomes -1 over x squared, and you know that one already, you could have just done that. So, you could have done so this is the same as x3 cubed times 1 over x2, and 1 over x2 would become that, according to this rule. So if you happen to know that rule, you could just do it. You can also use the quotient rule if you want.
Sorry, can you move the paper up a bit? I didn't get the F1. I mean, like, yeah. Oh, yeah, there. Thank you.
You're welcome. All right, let me try F13. So that means the 1 was done first, and then I did the derivative with respect to the third variable. What was that formula again? It was x3 cubed over x2, wasn't it? Yeah. And so now the dividing by x2 counts as a constant. So that will actually still be there afterwards. So multiplying by a constant is still there after you do a derivative. Dividing by a constant is still there after you do a derivative. So I can just leave it there because the x2 counts as a constant for this derivative. And then the derivative of this would be power at the front, and then it goes down by 1. So that one was a bit easier. I'm going to do one more of them. Let me do F31. Are we okay with that? So that would mean I'd do F3 and then I'd do the derivative with respect to x1. And the formula for F3 was earlier. Was that. And so I'm doing d on dx1. So the 3 is multiplied on, so it'll still be there. The x2 squared is a constant multiplied on, so it'll still be there. Oh, sorry, that's an x3. x3? Yep. The x2 is a constant divided, so it'll still be there. And the derivative of x1 is 1. Because that's the curve, yeah. Or the derivative of 3x1 is just 3. And then that doesn't have any x1, so its derivative is 0. And luckily, oh, actually, just because it always works this way, f1,3 and f3,1 have the same answer. I don't feel like doing the other ones. I've still got I've still got 3, 2 and 2, 3 and 2, 1, and I just don't want to do them. So I'm going to stop there if that's okay. If you were asked to do all 6 of them in your exam, then you would do all 6 of them. And you wouldn't say, I'm tired, I will stop. But I don't expect your lecturer to do that because there's only so much time. Or they won't ask this at all because you have to do partial derivatives in order to do some of the other problems. Yeah. But I'll do one of those problems now. Let me find it. All right. This may not turn out the way I want, but I'm just going to try. So I have 2 good. Firm is perfectly competitive. Sells G1 at $70 and G2 at $50. Total cost is Q1 squared plus Q1 times Q2 plus Q2 squared. I'm guessing that Q1 is the quantity of good number 1. Oh yes, that's what it says on my screen that the people online can't see. And Q1 is quantity of G1. Q2 is the quantity of G2. And the maximum profit. Okay, this is the problem we're going to work on. Okay, so the first thing I need to do is figure out what the profit actually is. What's the symbol you use for profit? Is it P, pi? Pi? Fun. Okay, so the profit should be the revenue minus cost. Is that right?
Yeah.
And so the revenue should be, there's this many G1s and they're $70, and there's this many G2s and they're $50, and then the cost is this. I reckon that's my interpretation. Okay. So the maximum profit should occur when the derivative is 0, but there's 2 derivatives that have to be 0, both at the same time, because there's 2 variables here. So I need both partial derivatives to be 0. So the maximum when that is 0 and that is 0 at the same time. Has to be both of them. So just like maximizing revenue when there was only one quantity, we needed the derivative to be 0. When there's two quantities, we need both derivatives to be 0. Okay, so let's figure out what they are. So that should be 70. That doesn't involve a Q1, so I'm not going to have that. And then I'll be minus 2Q1. And the derivative of that would be the number Q2, because that's the constant that's multiplied by Q1. And that doesn't involve a Q1, so it'll be 0. Okay? And d pi on dq2 would be 50 minus, that doesn't have a Q2. The derivative of that with respect to Q2 would be Q1, and that would be 2Q2. And this derivative, yeah, we did that. So I need both of those to be 0 at the same time. Now I have two equations and two unknowns, and you should be allowed to solve them by whatever method you think is best. You could use matrices, you could use simultaneous equations, whatever seems to appeal to you. I shall use simultaneous equations. So this one I'm going to rearrange in my head before I do anything else. If I put this over there and switch it around the other way, I'm going to get 2Q1 plus Q2 is 70. And this one's going to give me Q1 plus 2Q2 will have to be 50. Because the only way that 70 minus this number will be 0 is if this number is equal to 70. And the only way that 50 minus this number is 0 is if this number is equal to 50. And these equations feel nicer to me. So I'm going to have to solve those two equations simultaneously. I shall call them 1 and 2. Anyone got any ideas? I have ideas, but you know, it's your seminar. That where? You're all good? Sweet.
Could you multiply one of them by like a negative so that they cancel out?
Sounds like a plan. What do you want me to do? Multiply the second one by minus 2?
Yeah. Why not?
Like that. And then if I did now number 1 plus number 3, that would make these cancel out. Was that your plan, that sort of thing?
Yeah, that's how I usually do it.
So this plus this is 0. This plus this would be minus 3 lots of Q2. And this plus this would be minus 30. And now if I divide everything by minus 3, I'll get 10. Nice. Well done. And so now I'd sub that back into whichever one seemed easier to figure out what Q1 is. I'm going to sub it into number 2 because that's got a plain Q1 all by itself. So it'll be 50 minus 20, so that's 30. So if there really is a maximum profit at all, as opposed to a minimum profit, it will be at that spot where Q1 is 30 and Q2 is 10. Yeah, I mean, Desmos, yes, you could have graphed, you mean graphing the two of them? Yeah.
Well, I mean, we could have. I mean, you don't have to do it.
No, I'm interested. Where is my website? It is. So I don't want the matrix calculator. I want to go back to the. I think it will allow me to use Q1 and Q2. No, it'll have to use X and Y. There they are. And that's at Q1 is 30 and Q2 is 10, where the two lines cross. Good thinking. Yeah.
I was just thinking, like, you could, like, from the very beginning, just so revenue total cost, we put it into this.
Yeah, probably.
Yeah.
Well, no. This formula, it can't show me this formula because there's actually three variables involved. There's the Q1 and the Q2 and the profit. So until I've turned it into something that's only got two variables, my graph's not going to be able to do it.
Right.
Yeah. Yeah, let me show you something. So the profit, I'll just call it P, was 70 Q1, which I'm calling X, plus 50 Q2, which I'm calling Y, minus Q1 squared, plus Q1 times Q2, plus Q2 squared. And I can actually look at which points X, Y make the profit come out to certain numbers. I shall call it C. Oh no, it doesn't work. It's okay. Ignore that. I really thought it would work. No, it's worth a try. Ah, well. There we go. So this is the profit here, and this is coming out to be equal to the number C, and the number C is currently 166. And it does actually. And you can see that as the profit, the total profit gets higher and higher, that's somewhere in there is the last profit. And so these are the bundles of Q1 and Q2 that produce a profit of 0. These ones produce a profit of 600. These ones produce a profit of 1250. These ones produce a profit of that, and then they're narrowing in on this point, which is 30 and 10. So that's very fancy. This is essentially, did you do indifference curves?
Yeah.
This is the same sort of thing as an indifference curve, but this is like an equal profit curve.
Right.
And so you can find the maximum by figuring out where the equal profit curves get closer and closer together. So I wouldn't recommend it. It's not at all what the lecturer is thinking, but it is the same idea. Yeah. That was fun, thank you. Yeah. How are we feeling? We're doing all right. I reckon I'm going to now do a maximizing with two variables. Like we've done a maximizing with two variables already. what if I wanted to do a maximizing with two variables subject to a constraint? Because that's the last kind of problem. Just give me a minute to ponder some of the things. You've been very gracious hosts, thank you. I'm going to do this one first because it's about partial derivatives. It's not about maximizing, but it's still in the zone, so I'm going to do this one. Or maybe I should put my my paper back on the screen. Not that one. So we have a utility u, which is x1 to the half, x2 to the third. Okay, find the marginal rate of, I've forgotten what it was called, something, CS.
Commodity substitution.
Commodity substitution, okay. When x1 is 25 and x2 is 8. Okay. Should have worn my TLA t-shirt. Okay. So the marginal rate of commodity substitution is that. Is that right? Or is it the other way around? Or does it not?
The other way around, I think. Yeah, the other way around.
I mean, supposedly that doesn't really matter that much, but so it's the second one compared to the first one compared to the second one. So let me just check this. It's marginal, meaning it's a derivative. I've got that. And commodity substitution would be replacing the x1s with the x2s. That's what that phrase says to me, or the x2s with x1s. And so this is saying if you want more x2s, how much will the x1s go up or down by? And so this should be a negative number, usually, because if they're both goods, then if you want one more of them, then you'd normally want less of the other one. Like, isn't that how it normally goes? I don't know. Just going to make it up and see what happens. Okay. So how do you figure that out?
Because I think like some things depend on others, like some goods like Wi-Fi charger, you need to buy that with it, so they both go up together.
So is this assuming that the utility is fixed? I reckon I'm going to need an example for this because this is I've got thoughts. I have a guess that this is this. Could be wrong.
Want me to get the lecture notes up? I'll see if I can find them.
Yep, that'd be great. This is I have thoughts based on my understanding of derivatives, but I'm just not 100% sure, so I'm just going to have to make sure we look this up and get it exactly right. My instinct would be, my instinct is that the idea of this MRCS is that if you've got a specific bundle, it'll have a specific utility. Aha. The MRCS isn't dx1 on dx2, it's minus dx1 on dx2. Okay. Keep going. Okay, keep going. Oh, and that's now something new. Okay. What happens before this? Oh, is the marginal rate of what's TS? Technical substitution? I don't know.
Yeah, that's the technical marginal rate of technical substitution. But there's unfortunately no example for this one. That's why I'm really don't know how to do it.
All right, I'm gonna look at this formula down the bottom because your lecturer says that we apparently know this. All right, that's the thing I needed.
Sorry, I accidentally got it wrong.
That's all good. That's what I felt uncomfortable. So this makes sense to me. All right. Cool. So it's the speed at which the utility is increasing when x1 changes.
Is the microphone still on? Sorry, I can't hear.
That's weird. Just a second.
How's this sound? Or is that annoyingly strange?
Like really crackly and
Let me try this. How's that?
it's just really quiet. Like I can hear, but it's like I'm on full volume and it's like whispering. But I'll just
Sorry, my computer sometimes after a little bit just turns weird.
Yeah, that's okay.
Will here. All right. I can at least make my voice louder. Is that any better?
Yeah, that's good now. Thank you.
I put my microphone on in the lecture theatre so that the microphone in the computer can hear it. Okay. So this is how quickly the utility changes when x1 does, and this is how quickly the utility changes when x2 does. So if you change both of them simultaneously, you want to, this is to do with, I think there's all sorts of stuff going on. In my head, we're keeping the utility the same because we wouldn't want to change it usually. And swapping out some of the x1s for the x2s. And this will do the trick. Okay, so if we figure out the u was equal to x1 to the power of a half and x2 to the power of a third, and then du on dx1, the x2 to the power of a third is a constant multiplied on, so it will still be there. And then I'll do the derivative of this, which is a half of x1 to the negative a half. I might just leave it like that and not do anything else. And then the du on dx2, the x1 to the half is a constant now, multiplied on, so it'll still be there. And then we'll have 1/3 x2 to the minus 2/3, because I'm going 1/3 minus 1 will be minus 2/3. And then I have to divide those two. Which I do not like, but anyway, there are a lot of numbers flying everywhere there. All right, first I'm going to deal with that half and that third. If I multiply the top and the bottom by a 3, then the third down here will go away, because a third times 3 is 1. And so there'll be a 3 on the top. If I multiply the top and the bottom by 2, then the half will go away and I'll get this. And that does make sense because half is 1.5 thirds.
So can you talk through that a bit slower?
Yep.
I missed it.
I'm gonna just pull off and do the calculation with the half and the third separately. That's okay. A half divided by a third is the same as, if I multiply this by 3 and this by 3, which I'm allowed to do with fractions, then the half times the third will be a 1. And if I multiply this by 2 and this by 2, sorry, not half times a third times 3 is 1. And if I do the same with the half, a half times 2 is 1. So a half times 2 is 1 and 1 times 3 is 3. And a third times 3 is 1 and 1 times 2 is 2. Yeah. The other option is to know that dividing by a fraction is the same as multiplying by the fraction the other way up. And so I get this, which is much shorter. So I'm glad I've tried a different way. Is that all right?
Yeah, that's good. Thank you.
Okay. So therefore, my marginal rate of the half divided by a third is now a 3/2. So, since there's an x1 on both the top and the bottom, I would try and simplify it. This is totally a correct answer, but I'd try and simplify that. And it's tradition to arrange things so that you don't have any minus exponents written. And so multiplying by x to the minus a half is the same as dividing by x to the half. So that thing can be down here. And dividing by x to the minus 2/3 is the same as multiplying by x to the 2/3. And now when I multiply the powers, x2 to the third times x2 to the 2/3 is just x2 to the 1, because I add the exponents. And the same thing happens here. Oh, look at that. Cool. And I think that's a pretty good answer. And what did they want to know? They wanted to know at the point when x1 is 25 and x2 is 8. So if x1 is 25 and x2 is 8, then the marginal rate of commodity substitution, the x2 is 8 and the x1 is 25. And so I get that. 24 divided by 50, which would be 0.48, I think. Sorry?
Is that the same as 12 over 25?
Yeah.
This is one with questions.
So if we are, do we want it as a fraction?
Yeah.
So, whoa, the 2 goes into the 8, so I can divide them both by 2, and I'll get 3 times 4, which is 12 over 25. But if I want it as a fraction, a decimal, then that's what it works out to be. Okay. So this is seeming to say to me that for every 2 x1s that I give up, I would be okay to replace it with 3 x2s. Like for every 2 of commodity number 1, I'd be okay with replacing it with 3 of commodity number 2. That's my idea of the commodity substitution. But it's slightly different depending on what the quantities actually are at the moment. But something like that. No, that doesn't make any sense. So at this point, this is saying to me that I would, for every x1 that I give up, I'd be okay with having 0.48x. No, crap. Which one? For every x2 I give up, I would be okay with having 0.48 x1s in replacement at this point when I've got this many of each. Yeah, right. So in some sense, it looks like the x2s are sort of worth more to me in terms of how how much the utility is. Right. But if I had x1 being like 5 and x2 being a bigger number, then it would be the other way around, and I'd be okay with giving up on x1 and getting more x2s. Yeah. Yeah, this is, I think, the negative of the slope of the indifference curve. I just want to try that. Can I just give that a go? So we had u equals x1 to the half, was it? x2 to the third. So if I pretend u is a constant and rearrange this to get I'm just going to write it this way around. And then get x2 to the third is u divided by x1 to the half. And I'm just going to write that as u to the x1 to the negative a half. And then if I want to get rid of a third power, I'm going to have to do a power of 3. So if I'm going to be really explicit about it, this is what I'll do. And so x2, because 1/3, when you do powers of powers, you multiply the exponents. So 1/3 times 3 is 1. And this will be u cubed x1 to minus a half times 3, which is minus 3 over 2. And so now at this point, if I do dx2 on dx1, I get the u cubed counts as a constant. I'll multiply by the current power and put the power down by 1. Wow. And you can see that minus 3 on 2, that's where that 3 on 2 is coming from the other one. I really hope that these are the same thing. So I'm just want to try something. If x1 is equal to 25 and x2 is equal to 8, then that means that u is equal to 25 to the half, because that's what this formula is, times 8 to the third. And a half is the square root, so it'll be 5. And a third is a cube root, so it'll be 2. So the u comes out to be 10. And then dx2 over dx1 would be minus 3 over 2 u cubed x1 to the minus 5 on 2. The u is 10. The x1 is 25. Wow. I really haven't made it easy for myself. So that's 1,000. Now 25 to the half would be 5. And 5 to the power of 5 is a very large number, which I don't know what that is. But I'm just going to ask my calculator what this works out to be. which is exactly, oh, gotta love it, minus 0.48. Yes! So it looks like the marginal rate of commodity substitution has two formulas. It's du on dx. One, was it? Damn it. Where's the beginning of this working? That's my working. Here it is. Du on dx1 divided by du on dx2. And it's the same as minus dx2 on dx1. So this one's straight from the utility, and this one's straight from the indifference curve. Right, so that's the thing. If you're given the utility and you want the marginal rate of commodity substitution, then you can figure out that directly from the utility like this. If you've got the indifference curve and not the utility, then you can figure it out like this. Yes. This excites me. That sounds like such a thing that a lecturer would do, like to give you one or the other and you'd have to know both. But I don't really know. I'm sure there's some theory, and maybe this is more like the sort of thing that happens in microeconomics too. Because microeconomics is, that utility curve is a microeconomics thing, the micro referring to individuals, as opposed to macroeconomics, which refers to populations. Yeah. So my understanding of it, so I haven't studied economics, I just help people with it. My understanding is that that supply and demand curves are macroeconomics, but utility and indifference curves, they're microeconomics. Because the supply and demand is about the whole market, and utility is about how an individual feels about what commodities they have. Yeah. So now you've got the maths of both, you'll be able to do those things in the future. All right, one last example. Not that one. All right. Consumer's utility, sorry, is U, which is 4 times ln of x1 plus ln of x2. Find x1 and x2 so that U is maximized, subject to the budget x1 plus 2x2 equals 100. There are many ways to do this. I'm imagining in your lecturer probably is thinking Lagrange multipliers. Is that Lagrange method? Is that a thing? No?
Yeah, that's what we usually use.
Yeah.
Yeah.
Okay. So there is another way to do it, which is to rearrange this to figure out what x1 is in terms of x2 and sub it in. And then just straight up differentiate with respect to one variable. They should both work, but the Lagrange multiplier thing is the classic, because it works no matter what crazy thing is going on here without having to sub anything in. Okay. This is how I would do it, and feel free to tell me if this is different to something you've seen. I'll get the utility. and I'll take off a multiple. I normally use the letter lambda. Does that sound familiar?
Yeah.
Am I supposed to, does your lecturer normally put a minus, or do they not care?
Let me just check.
It probably doesn't matter, but sometimes it does. So ultimately, you want to change this into something that's about being equal to 0. So you go, that's the same as x1 plus 2x2 minus 100 equals 0.
Oh, I think, yeah, he usually, it's a plus, and then he rearranges it so it's like all minuses in the brackets.
Okay, so he puts a plus here and he puts 100.
Yeah, like that, I think. Yeah.
Cool.
Yeah.
It does, you'll still get the right answer either way, but it's nice to do it the same way your lecturer does it because it'll match with his solutions. I don't know how your exam works and whether you're uploading handwritten solutions or not. So the first step of the working, sorry about that, is actually, you can do it in your head, but we're basically trying to make my constraint about being equal to 0. And so we're saying, well, if this is the budget, this is how much I've spent, and it's equal to the budget. And so I'm imagining that the budget minus the amount of much I've spent would be how much I've got left. So the idea behind this is to say, well, what if I didn't spend the whole budget and then I'd still have some money left, basically. 100 minus the amount of stuff I spend is the amount of money I've got left. Or if it's not money, it could be anything, but this amount of, I'm going to say money, the amount of money I've got left. And the lambda's there because Lagrange had this cool idea, and so we're just going to run with it. Okay. So this is now a function of 3 variables. It's got the x1 and the x2 and the lambda as well. Finding the maximum of this function is the same as finding the maximum of this function. Like if this really is equal to 100, then this will be 0. And so whatever maximum this has when this is equal to 100 is the same as the maximum that this has. So that's the idea behind it. It'll work out to the same answer. So short version is that finding the maximum of L is the same as finding the maximum of U. So I need all 3 derivatives of L to be 0. Like that. Very, very clever of Lagrange to create a brand new variable to help solve the problem. So to take it from a function of 2 variables to a function of 3. Okay, so I'm going to figure out what those 3 derivatives are. dl on dx1. Okay, the 4 is multiplied on, so it'll still be there. The derivative of ln is 1 over thing. This doesn't have an x1, so that'll become 0. This lambda is a constant multiplied on, so it will still be there. And the derivative of this bit is 0, minus 1, and 0. And then dl on dx2. That doesn't have any x2, so it'll become a 0. That one will become 1 over x2. And that one, the lambda is multiplied on, so it'll still be there. And the derivative of this bit is minus 2. And they both have to be 0. And finally, dl on the lambda, that doesn't have a lambda, that doesn't have a lambda, and this is the constant next to the lambda, so it will be that constant. And it always works out that this is the same as the original constraint that we wrote down, basically. So, from number 1, I can get that lambda must be equal to 4 on x1. So it's this minus lambda equals 0, which means that this must be equal to that. And from number 2, I get that 2 lambda is equal to 1 on x2. There are many ways to deal with this, but the ultimate goal is to get rid of the lambda. We created the lambda in order to help us solve the problem, but it's not really a real thing. I think there is a technical meaning for what lambda is, but I don't care. The point is to try and get rid of the lambda because it wasn't in the original problem, so we don't need it in the final answer. And so I can do it by whatever method I like. For example, I could sub this one into there, because lambda is 4 on x1, so I could replace that with 4 on x1. Or I could go this one divided by that one, and 2 lambda divided by lambda is 2, and this divided by that is whatever it works out to be. So I get to choose how I deal with that. I'm going to sub one into the other. So I'll get 2 lots of 4 divided by x1 is equal to 1 over x2. So I put this there instead of lambda. So now I've got 8 divided by x1 is 1 over x2. And if I flip them both upside down, well, maybe what I'll do is I'll times this one by x2 and this one by, and so times everything by x2, which will put the x2 at the top on this side, and times everything by x1, which will put the x1 on the top on that side. All right. So now I can look at the constraint. I need x1 plus 2x2 to be equal to 100. And I can sub this in. I will call it number 4. So x1 is really 8x2 plus 2x2 is 100. So 10x2 is 100. And I fell off the edge of the page. And so x2 is really 10. And then I can sub that back into whatever I want to try and figure out what x1 is. So I'm going to sub it into number 4, because number 4 said x1 equals, so which is 8 times 10, which is 80. So the maximum occurs when x1 is 80 and x2 is 10. They didn't actually ask us what the maximum utility was, so we're just going to leave it at that. But if they wanted to know what the actual value of u was, I'd take these numbers and I'd put them back into the original formula. How do people feel about what happened there? Is that one of the ones you sent?
I know I sent that one, but yeah, that's good. Thank you. Would you be able to just move the paper up a bit? I didn't get the. Oh yeah, I did that right. Okay, thank you.
So there's lots of maximizing that we did there. We did a few other things, but they are all things ultimately to do with derivatives, which is good. It's like that means I can have a title on it when I put it online. It was mainly maximizing things. So if you don't have a constraint, then you just need the partial derivatives to all be 0. If you have a constraint, then you add an extra variable, which is the lambda, and make all the partial derivatives 0. And that allows you to not have to figure out what one variable is in terms of the other. So I could have, if I wanted to, I could have actually gone, oh, well, x1 is 100 minus 2x2 and sub that into here and just done du on dx2. And that would have also worked. But I don't think that's what's in your lecturer's head when they set this up. Yeah.
Is there an advantage to it this way or that way?
Well, this way will work better when this is more complicated. Because already you have to use the chain rule when I sub this into there. And imagine having something here where some of the x1s are times by the x2s and the derivatives would get worse and worse. And it's actually slightly easier to do partial derivatives than to sub in and use the chain rule. Yeah. Yeah, and then it also means you don't have to rearrange this formula either. So there's less scope for getting minuses and powers in the wrong spots. Yeah. But also this means that if your budget constraint isn't a straight line, I mean, budget constraints are always straight lines because that's how budgets work. But if you're in another context where the constraint you're thinking of isn't a straight line, because it came not from a budget but from something else, then this would be easier than rearranging that formula too. Yeah. But with utilities, it's almost always budgets, and budgets are straight lines because that's how budgets work. Yeah. Any other things before I sign off? Happy to stay for a few more minutes.
I just have one last question, sorry. Would you be able to quickly run through implicit differentiation?
Ah, probably. So my understanding of implicit differentiation is when you have something like, I had one. I could have done that with implicit differentiation. That would have been cool. So that one. So what if the utility was equal to just a specific number? What did the utility work out to when we did that? Was it 10? Okay. So I'm just making stuff up now. It's not an actual problem. But an implicit derivative is knowing that this equation should produce a graph of some sort. And if I'm very close to a specific spot, I should be able to rearrange. It should theoretically be possible to rearrange it to get x2 equals function of x1. And we actually did that in our calculations earlier. But you can figure out the derivative of x2 with respect to x1 without actually rearranging the formula. So we're going to imagine x2 is a function of x1. That's what we're imagining. And then we're going to do the derivative with respect to x1. So we're going to do d on dx1 here. And we're going to do d on dx1 here. And this is not a partial derivative, because I'm imagining that inside x2 here is some crazy formula that tells me how x2 is a formula based on x1. So this is 0. And these are two things multiplied together, so I'm going to have to use the product rule. I've got the derivative of that bit, and I'll keep this bit, plus keep this bit, and do the derivative of this bit. Okay. The derivative of that bit is a half x1 to the minus a half. And the derivative of that bit would be a third x2 to the minus 2/3. But x2 secretly is a function of x1. So because of the chain rule, I'm going to have to multiply by the derivative of x2 with respect to x1. How do you feel about that move that I just made?
So you're doing that because of the chain rule?
Yeah. So this plus was because of the product rule. But
Okay.
this bit here was because of the chain rule.
Oh, yeah, I see. Yeah.
Yeah, because the x2 is secretly a function of x1. I just don't know what the formula is. And now I have this, which is whatever it is. And usually what you do at this point is you'd start rearranging it to get dx2 on dx1 equals something. And so I'd get, it's not pretty, is it? I'm just going to move this over here. And then I'm going to divide by this. And this is the exact same expression we got last time when we did it via partial derivatives. Yep. And so what this does is it gives me a formula. We already did the calculation for this, so I'm going to skip that bit if that's okay. That gave me 3/2 like that. And so now if I'm at a specific point, if I know both what x1 and x2 are at that point, I can sub them in to get the answer. I'm going to do another example because this one is less clear than I was hoping. What this does show is that I could have figured out the dx2 on dx1 via implicit differentiation instead of rearranging to get the indifference curve. Okay, I'm going to do another example just to make sure. What if, I'm just going to use x and y if that's okay. So here is an equation that relates x and y. And I want to know, give me a second. Give me a sec, I'm just going to do some calculations to make sure I do this correctly. Now, I'm just going to change this number if that's okay. It's very hard to create these formulas. No, just a second. One. Yeah, I was right. Okay, when y x1 is and y equals 2, find dy on dx. This is a classic implicit differentiation problem. Does this look like something you've seen before?
Yeah.
Okay, so first you have to check that this really does satisfy the equation, because otherwise all bets are off and there's no point even doing it. Okay, because the assumption is that we can only find dy and dx if they're part of this formula. So I'm just going to check when x equals 1 and y equals 2, 1 squared plus 3 times 2 times 1 plus 2 cubed is 1 plus 6 plus 8, which is indeed 15. Phew, it's almost like I set it up that way. Okay, so this point actually is on this curve, and so that's okay. And so then what I need to do is I need to do that same trick that I did last time. I'm going to imagine that y is a function, that inside the y is a function of x. There's all these formulas, I don't know what the formulas are, involving x inside the y. That's what I'm imagining. And so I'm going to do the derivative with respect to x on both sides. So to be absolutely clear, okay, so the derivative with respect to x of that is 2x. This one involves two things multiplied together, and that y isn't a constant, it's a function of x, so I'm going to have to use the product rule. So the 3y, the derivative of that would be 3 times whatever the derivative of y is, and I'll keep the x, plus keep the 3y, and the derivative of x is 1. And then the derivative of 3y of y cubed is 3y squared, but the y is really a function of x, so I'm going to have to use the chain rule and multiply by whatever the derivative of y is. And that will come out to 0, because the derivative of a constant is always 0. How do you feel about what happened there? Yeah? Tell me more. Yeah? It's been 2 hours. But yeah, in my head, I'm literally covering this up and thinking what would happen if it was x squared plus 3 times crap x plus crap involving x cubed. And the derivative of this would be 3 times that stuff squared, but the chain rule says I'd have to times by the derivative of whatever that is. But I don't know what that is, it's just called y, so the derivative of that is just called dy and dx, because I don't know what it's called. Yeah, that's what I'm thinking. And now the goal is to get dy and dx equals, and so what I'm going to do is going to rearrange this formula to get dy and dx equals. So I'll remove the bits that don't involve dy and dx and put them over there. And then I'll notice that these both have a dy on dx, so I'll factorize that out. And then I will divide by that now that it's just dy on dx times something. And now I have a formula for what dy on dx is. Unfortunately, it's not like a normal formula for dy on dx, which would involve only x's. It's a formula for dy and dx that involves x's and y's. So I have to know both what x and y are at the same time to be able to figure this out. But that's okay. I was told that when x is 1 and y is 2, dy on dx works out to be minus 2 times 1 minus 3 times 2 over 3 times 1 plus 3 times 2 squared. So you use both the value of x and the value of y to figure it out. So what's that? That's minus 2 minus 6, so minus 8 over 3 times, that's 15. So that's what it is. It's not particularly edifying. What I'll do is I'll draw one more thing, but before I do, anyone got any questions about that?
No, that's all good, thank you.
I will draw one more Desmos graph.